So I said first, the study of motion with respect to the force causing it is known as dynamics. Then I said that this dynamics is also known as the laws of motion. And I said that the laws governing motion was worked on and proposed by a man known as Isaac Newton, Sir Isaac Newton. And the first law he gave is known as the law of inertia. And inertia is simply equals to mr squared. So we say that the first law talks about the tendency of a body to continue to rest or to keep moving until it is stopped. So if that is the case, you need to know also that inertia can also be said to be the reluctance or tendency of a body to move. So the reluctance of a body to move. So the reluctance of a body to change its position is also known as inertia. So if a body is at rest, it will want to stay at rest. If it's already moving, it will want to keep moving until acted upon by external force. So that reluctance that it exhibits is what we call inertia. And we normally say that inertia is given by the formula I equals mr squared. So first law states that the body in motion continues to move, and if at rest, remains at rest until acted upon by external force. The second law of dynamics, this law simply talks about the rate of change of momentum. So the law states that the rate of change of momentum, the law states that the rate of change of momentum is directly proportional to the applied force. The rate of change of momentum is directly proportional to the applied force. So this is the law. The force is directly proportional to the rate of change of momentum. Momentum is simply product of mass and velocity. And anything that has to do with rate of something means divided by time. So if that is the case, that means that this is something as F directly proportional to mv over t. Now remember that k is the constant of proportionality. So if we introduce equality sign, k comes here. And this k will be 1. So if this is 1, I can simply say that that is kmv over t. I can simply say that I can just ignore it so that this becomes mv over t. And v over t, velocity over time, is simply acceleration. So me. So what this law is simply trying to say is that if I push something this way, if I push something like to my left, that thing will go to the left. Force simply means push and pull. So if I push something to the left, it will go to the left. If I drag it forward, it will come forward. So it's trying to say that every particular body or object will move in the direction. Acceleration means direction. So change in movement will move in the direction of applied force. So that is what the second law is talking about. So it's that second law that gave us the formula we normally use for force. So the third law, mass acceleration, yes. So where m equals mass and a equals acceleration. And you know that mass is simply the amount of matter a body contains. Acceleration is change in velocity, so we say direction of something, change in direction. So the third law.
Is it 1?
Yes, it means proportionality constant is 1. K is equals to 1. Yes. So it's not always, but in this case it's equals to 1. So number 3, the third law. The law simply says that to every action there is a reaction. So the law is saying that the force applied to a body, will bring about an equal and opposite reaction. So the third law is saying that force applied to a body brings about an equal and opposite amount of reaction. So it's more like saying if you slap the left the person wants to slap the right. So there will always be a reaction to every action. The fact that you are standing because as you are standing, the earth is exerting an upward force on you. The same thing with when you are moving. If the floor can't hold you, if it's slippery, you will just fall down. But because there is friction acting on you backwards, that's why you're able to move forward. So this law is simply saying, in terms of equation, this law is simply saying that F is equals to reaction. F is equals to reaction. So that is when I have just one force. And another way to look at this is that this law, this third law, is trying to say that everything that happens will always have a force. So if I say, for example, that two cars are like in a setup, and at the end of the day, one car is towing the other one. In this case, for the fact that this one is moving, it means that the force on this is the force that the throttle is giving to this. Is moving. Now, for every rope you have, there is tension. So on this rope, there is tension, and tension is another name for force. The force on the rope is known as tension. So force on a rope force is known as tension. So if that be the case, for this particular body, the force is on this body is simply the forward force. This forward force minus this particular force on this thing now, this object as it's moving, this rope, because it's dragging this rope is trying to take it down. But if the force is more, it will keep moving forward. So the forward force minus the backward force, which is tension, equals to force. And force is ma. So this third law is trying to tell you that everything you have that experiences movement, that there is a force on it. So for the fact that this object is moving, there is a forward force to it. And because there is a rope tied to this particular car, there is a backward force. And the whole force there is equal to the total force. It's not like saying, is there force there? Yes. So force is equal to what? The total forces. So that is for this particular car. Let's say I call this car M1. Now for the second car, assuming they told you that friction is here, in most cases they tell you ignore friction. So this is like for M1. Assuming they said there is friction on this second body. Assuming they said there is friction on this second body. In that case, the force is on this body will now be this forward force, which is tension. Now the backward force here will be friction. It will now be forward force minus friction equals to there is force, total force. But in a situation where you notice that the question read and did not mention friction, yes, we know every day we are experiencing friction, things that are happening. So it's not like saying we ignore it. That means the last body on any horizontal surface will always be just T equals to MA. Welcome.
Sure, sir.
Yeah, welcome. I greet you. T equals to MA. And this T now, this T is simply tension on the rope. So for M2. So what this thing is trying to show you is like for horizontal bodies. I know I'm being too fast, but I will recap. So for horizontal bodies, when it's vertical, we'll come to that. So see what I'm saying. I said in the third law, we are trying to say that everything that goes forward, everything that you do, let's say you push somebody, as you push that person there, your hand will feel an effect. That is why if you push something that is heavier than you break your hand. Yes. So because that particular heavy something, let's say you use speed and run to this wall, hit it, and you use too much speed, because this wall will always stand still, your hand will just it's like maybe somebody that jump from roof building. The minute you fall to the ground, your limbs might enter inside your stomach because the floor will exert equal force on you backwards. So it's just the same case. Forward force will equal to the backward force. That's what we are trying to say here. So if it's just a situation where you now have more than one force, So a situation where you now have more than one force is not just going to be this setup again. It will now be that if you have more than one force, analyze each body, check the forces on each body, analyze each body, check the forces on each body. So if I have, let's assume I have like 3 bodies, horizontal, when it's vertical it's different. So if I have, let's say, 3 bodies now, and maybe it's being tied with a rope, we'll have cases where, assuming it's not tied with a rope, that means it's just one body we are looking at. So we always connect rope to it so that we say that we have more than one body. So let's say it's not really possible, but let's just assume that we have 3 bodies, and these 3 bodies, the first car is towing the 2 cars. Now, for this car to be moving, for the fact that this car is moving, there is a force on it. And that force on it is simply the force that the engine is exerting to move this car. That's the forward force. Now there is force on this rope, which is the tension force. There is force on this rope. So let's call this one T1. There is T2 here. Another force on this. Now what I'm saying is that unless the question mention that there is friction, if the question does not mention friction for anybody or object that is horizontal, the last body will always, the last one, let's say this is M1, M3, M2, M1. So for M3, provided it's horizontal, the last body will always be, in this case, T2 equals to the mass and acceleration. This means equals to the force. So the T2 is the force in this system. But assuming maybe there is friction in this setup, that means that friction will be here. It will be on the last body. So that you now have T2 minus F equals to, because friction is simply the force that goes in opposite direction to motion. If something is moving forward, friction is going backwards. If it's moving up, it can't be friction, it will not be gravity. So if that be the case, the last body, so this will be T2. T2 equals to, this is mass 3. Now for M2, for this body, M2, for M2, the forward force here is T1. Now there is backward force, which is T2 minus T2, equals to the mass here is M2 and A. MA means force. So it's more like saying the whole force here. It's more like saying T1 and T2 is equals to the total force. That is it. Now for M3, the forward force here is F. Backward force minus T1 is equals to the total force. So it's equals to F. But you can't just say F. So it's just, you have to indicate, because this is for M1, because this is a different mass, M1A. So that is why we specify it that way. So you need to note it. So this is how to go about any particular force calculation when it has to do with dynamics and that body is horizontal. But it's not always that you have just horizontal. You can have when that body is at an incline or vertical. So let's look at, we have treated case of horizontal. Let's look at case of vertical. Let me get something to write. Okay. So for vertical body, when the body is vertical, I can clean. So for vertical bodies, in that case, we are no longer looking at what's it called? Just T and tension alone. In this case, we are now considering weight as well, because anything that goes up, as it's coming down, gravity will be pulling it down. In that case, weight comes to mind. So for vertical bodies, we need to understand how to view the setup for vertical bodies as well. So for vertical or pulley, vertical bodies or pulley connected bodies. So in this case, let's say I have like an illustration on how the question normally comes. Let's say I have something like this, and I have this to be the first mass. Let's say this is M1, and let's say this is M2. If you look at these two, you will see that M1 looks bigger than M2. So for that reason, if M1 is bigger than M2, it simply means that if you allow this thing now, let's say you are holding it, you allow it as it is, you will see that even if it maintains balance, at the end of the day, this one will go up, even if it doesn't fall off, but the weight of the whole thing will tend towards the side. It will tend towards the left, not the right. So for that reason, in dynamics, I always tell students, consider each body separately. Don't come and mix it up. So I will come to this M1, find the forces on it. Come to M2, find the forces on it. And to do that will simply be, I'll say, the tension here will be coming down. While the tension on this one will be going up. There is T here. There is T here. It is the same tension. It is the same tension force. It is the same tension force that will be acting here. The same tension force. You know that the other one, I did that because it's holding the first thread. But here is just two. So it's the same tension. The tension this one will be feeling will be due to this one. And the tension this one will be feeling is due to this one. The weight is carried from this one. So for that reason, I will say the total force here will simply be T. The T of this, which is F, and in this case, the F now, watch something, the F that I'm having here is simply going to be weight. Instead of F, it will be this M1, and because it's vertically placed, it's coming down, gravity is acting on all these things. Gravity tends to act on anything that is above the Earth's surface. So it will be M1G. Now, because it's coming, so it will be minus T equals to the total force. And this total force is simply M1, mass of the first body, and the acceleration. So it's the same as saying weight of the first body minus the tension equals to M1A. So this is another way to view it. So for vertical bodies, it's simply weight minus tension equals to M1 MA, or tension minus weight. So the bigger body is pulling this. So tension in this case is the backward force, because as it's pulling this one is exerting weight on it, but because it's more, it's going this way. So that means the tension wants to go this way while the weight is dragging it down. So, but for this particular body, the tension is going up, the tension is more, while the weight is less. So, it's going to be T minus the weight of the second body is equals to M2A. And this is the same thing as saying M2G. T minus equals to M2A. So whenever the body is vertical, whenever you hear an inextensible string or whatever is attached to a pulley, or whatever the system says, but you just notice that it is set up in such a way that it is vertical, it is hanging, it is vertical, do not say inclined, vertical. This is the idea to use. The bigger body's weight minus the tension is equal to the total force. While for the smaller body, the tension minus the weight of the smaller body is equal to the total force. So we also have the case where we now have vertical and horizontal connected to a pulley at the same time. This is where we have vertical body connected to pulley. Vertical body. So when I now have, for example, let's say, okay, are you done with this? Yes. So we need to note all these things, then we solve calculations on it. When I have let's say a setup, for example, here I have, let's say I have a body of mass on a table or on a flat surface, and it is attached to an inextensible string that runs to a pulley. So let's say this is a body of mass. And then let's say we now have another body of mass. You know that if for example you place this and this two, so this is more like when you have vertical and horizontal setup. So vertical and horizontal bodies connected to a pulley. Vertical and horizontal body connected to a pulley. So when you have this kind of setup, what will happen is that even if it's not this close, however it is, but what we know is that once you have this setup, the idea is to remember that if they are the same weights, that means this one will tend to move while this one will shift a bit. Let's say it was here, it shifted till it now stops here. You know that if the weight of this thing is too much, it can actually drag this thing and it will fall off. But in a situation where they are of equal weight, or maybe this one is lesser, it will drag you to a point and then it will stop. But as it is here, even if this one is lesser, this one is going to be comfortable, but this one will continue to give tension to this thing. So if that be the case, the one that is on the vertical will always be, let's say this is M1G, that is weight, minus the tension on this is the same thing, so it is going to be in this order. So minus the tension is equals to M1A, that's M1A for this particular body. While for M2, it will simply be in this case, because of the fact that tension is moving before it, so you say that it is tending towards tension. So it is going to be dt, but this time around, notice something. It cannot be t minus weight. It cannot be t minus weight. Do you know why? The weight of this thing is acting this way for this particular object. Weight of everything is acting vertically down. The same thing with this one. So this one's weight cannot be, is this way. So it has nothing to do with this movement.
Yeah, that's correct.
So for that reason, the only thing that is supposed to be acting on this against this particular tension is the friction. So assuming they mentioned friction in that question, is simply going to be this tension minus friction is equal to, so from that third law, what that third law is simply trying to do for us is to get all the forces, that is, get the forward and the backward. Forward from backward is more like saying if you are going to the east is positive, if you are going to the west is negative. Forward minus backward equals to the total thing. So that is just what we are trying to do in this case, equals to M2A. But since they did not mention friction, and in most cases they don't mention it, so for that reason, whenever it's horizontal, without stressing yourself, always know that horizontal force is always going to be just that force equals to MA, provided it's the last force there. So the last force will always be in a situation where it's expecting to have friction, but if it's not there, it's just C, in this case, equals to M2A. So this is the force on this particular body. Why? This is the force on this particular body. So whenever you have this, by the time you do it, another thing I need you to note, because we'll take an example. I forgot my question, but I'll generate a question from my head. So another thing I need you to know is that any question that has to do with dynamics, once you are given a question that has to do with dynamics, and they start asking you, most of the questions they will give you, they will not tell you, show that acceleration is equals to this. Then show that tension is equals to this. All you just need to do is just like I've done this thing now. Set it up in such a way that you can find the acceleration. See what I mean? Let this be equation 1. Okay. Let this be equation 2. At this point, remember the first rule. Find the forces on each body separately. Secondly, to find the acceleration here now, you now do, let's say this is now M1G. Let's say this is now M1G minus T is equals to M1A. And this is T equals to M2A. In this case, you always combine the two. Guys, so that at the end of the day, you use either elimination method, to get your A. So you see that this is going to be, if I add this up now, minus T plus T is 0. This will now leave. So that I now have M1G is equals to M1 plus M2 all A. Because if A times M1 equals M1A times this equals M2. So you can see that this is now going to be the same thing as, I know that this is plus 0, which is not it. So this is M1G equals to M1 plus M2A. So by the time you try to make A subject of the formula, you see that you can divide both sides by M1 plus M2. Divide both sides by M1 plus M2. This will cancel this. So that by the time you check it, you see that the acceleration is going to simply be M1G all over M1 plus M2. And this is the same thing as saying weight of the first body all over M1 plus M2. So you can see a question, and that question will tell you that if you have this setup, that you should prove that the acceleration is equals to this, then prove that the tension is equals to this. So once I've gotten this acceleration, carry the acceleration, substitute it inside any of the equations to find tension. So carry the acceleration, substitute inside any of the equations to find tension. So I'll substitute in equation 2 because it's simpler. So that, but if you do it even in the two of them, it will be the same answer. So I can just say T will be equals to M2, and A is simply M1G all over M1 plus M2. So that the T is simply equals to M2 M1. We say M1 M2 G all over M1 plus M2. Very simple like that. So that is it. So
is this one included? This is equals to that.
is it which one?
Is it included?
This one. This T now, this particular T equals M2A. That I'm trying to find the tension using this. So I went to do for this T, where I see the A, I replace the acceleration I've gotten there. This acceleration here, I replace it. Then use it to times this. So this can also be the same thing as saying M2 W1 all over M1 plus M2. So is this equation? What I did is just, this equation is this thing. I just replace the acceleration with what I have for acceleration. So before we start calculation, let's treat when we have the forces on an inclined plane. So you can very well see that third law is what is leading us. So the first law is on inertia. The second one is the law that gives us what we have when we talk about force equals to ma. So this particular one now is the law that gives us everything that has to do with forward and backward. So see, for inclined plane, for anybody of mass on an inclined plane, you can't say you have two masses on an inclined plane, their movement will be the same thing. So when you have an inclined plane, have it in mind that anything that moves in this direction on an inclined plane is known as mg sine theta. Why? A situation whereby a force is mentioned, if they tell you that there's a force on that particular body, the force will be in this direction. Now, if that is the case, if they give you just this setup, they tell you that there's a string or rope pulling this up, and then the body will want to slide. The part sliding is known as mg sine theta. So if you've known that, that is the x-axis. And the reason for that, those days, I will normally do all those derivations, which I don't want to do now. We say that weight goes this way, then this particular body, there is the normal reaction. As there's reaction on this up, there's normal reaction going downwards. Then, if that be the case, this is weight mg. So if that be the case, this is like, let's say this is the x-axis and this is the y-axis. So if you bring out what you've achieved here, you've achieved another triangle here. So you now come and say, yes, here, this thing is that mg. So it's not like saying this side now becomes mg, this side now becomes y, this side now becomes x. I really hope you can see what I'm doing. So if that be the case, remember that this y-axis is the part that gives us n. So that means that this is n, and x has nothing to it, but this side is the mg. So if that be the case, let's say the angle. Okay, in this case, the angle is here. Reason why the angle is here is because the angle made with that object is this angle. So in that case, we can now say if this is the angle, the side facing any angle is the opposite. So using SOHCAHTOA, opposite here is simply going to be opposite over hypotenuse. The opposite here is x. The hypotenuse is mg. So making x subject of the formula, remember that this thing s that is here is sine, O is opposite hypotenuse, so this is sine theta. So making x subject of the formula, you now have mg sine theta equals to x. Why, if you want to get n in this case, the side that is not opposite, but let's say I did this thing from what I taught you, the side close to the angle is adjacent. So cos, or you say tan. So C for cos theta equals to adjacent over hypotenuse. So equals to, the adjacent here is y, which is n, and the hypotenuse is mg. So we say that making n subject of the formula cross equality sign, it will now be m, that is, you do cross multiply mg cos theta equals to n. But if you don't want to stress yourself finding this thing, because nobody will ever ask you to start proving this thing. If you don't want to stress yourself proving this thing or finding this thing, all you just need to know is that once you have an inclined plane, this side is the x-axis. Everything happening here is mg sine theta, because weight of this is moving down. If the weight of this is moving down, that means that for the fact that it's moving down, weight is moving down, that is weight is acting here mg. Now, this is the x-axis, is sine theta, mg sine theta. While anything that is on the, what's it called? On this end, which is the normal reaction, is going to be mg cos theta. So, if you know that without stressing yourself, you can simply just say that to get the force on this object as it's moving this way is going to be, if this object tends to move up at the end of the day, the force here is more than this one, it will not slide. So if it tends to move up, it will now be F minus mg sine theta will be equals to m. So the mass of the object, that is, will be equals to the total force ma. But if this particular object, even with the force applied, tends to, so this is moving up, upward movements. But if at the end of the day, the object tends to slide down, that means that this one is bigger than the force. So it will be mg sine theta minus F equals to the total force. So note that. Note that. So that is for the first case when there is no friction. We can have a case where there is. Okay, now see here. Notice that everything we've done. Notice that everything we've done here, we did not make mention of friction. Okay. But there are questions that can be given, and in that question they will tell you that there is friction. So if there is friction acting on this, but let's say they give you a question and at the end of the day they tell you, taking note of the fact that there is friction on the object or on the surface. So assuming there is friction on this surface, what will now happen is that any part that is, if it's moving upwards, let's say upwards with friction, upwards when there is friction, so with friction, so upward with friction. In this case, what will happen is that if it's going upward, friction always go in the direction that is opposite to movement. So in this case, it will now be F minus, so x-axis is mg sine theta plus F is equals to ma. So this means that this is F minus x is the same as mg sine theta plus friction is equals to ma. So in this case, since the x is always wanting this to slide down, so in a situation where it's moving upward, friction will be going against it. So that means that friction and this body will be in the same direction. That is friction and the one and sliding, the tendency to slide. This thing is sliding tendency will be in the same direction. But a situation where it's going downwards, friction will now want to be going, will not be going in the opposite direction. So friction and F will not be in the same direction when it's going downwards. It's a situation where you have friction. So for that reason, downward with friction, or you say when there is friction, or when you are considering the friction, in that case it will now be mg sine theta, or you say x minus f plus f equals to ma. So minus f plus f equals to ma. And you need to know something. This f that is here, friction, we normally say that friction is the same thing as friction is equals to, first of all, friction is directly proportional to the normal reaction. Friction depends on the nature of surface. If the surface is very rough, friction will be high. If the surface is smooth, friction will be a bit not as compared to when the surface is rough. Because what causes friction is because of smoothness of the surface. So in also noting that as well, you need to know that friction will always be directly proportional to the normal reaction. And if that be the case, if I introduce equality sign, it will now have proportional coefficient of friction. It can be static, it can be kinetic, and then R. R means normal reaction. In some textbook you see it like this as N. So if you want to, you can say it this way. So let me use N. And remember that when I started this class, I first of all told you that that third law of Newton is saying that force is equal to normal reaction. So every action there's a reaction. So it's the same thing with friction. So friction is the same thing as force, but force that opposes motion. So if that be the case, and remember we found N here, we did something and we found N to be mg cos theta. So it means that I can replace this with mg cos theta. Then mu equals to this. So if I choose, I can also see sometimes that this thing, I can replace this. I can also replace this to now be the same thing as saying f minus mg sine theta plus mu mg cos theta equals to ma, or it can also be the same as saying f minus mg sine theta plus mu n equals to ma. So depending on the question given, all these things depend on the way. If they gave you maybe coefficient of friction and normal reaction, you just use this one. But if they gave you maybe mass and then you know gravity is constant, then they gave you mu, you can use cos theta for it. So as you start solving question, you will see how the questions look. But the main thing is getting the formula. So that means that in this case, this can also be the same thing as saying mg sine theta minus f plus mu n equals to ma, or mg sine theta minus f plus mu mg cos theta equals to ma. Is it plenty? So I will explain. So let me clean this part. Just copy, sir. I'll take time to explain. So see what I'm saying is, if they tell you that the surface has friction, That means that it simply means any direction the body is moving, the friction will be going in opposite direction. So a situation whereby they say it is moving upward, and what is making this thing to move upward is this. In that case, friction will not be in this direction. If it's moving upwards and they say there is friction. So for that reason, remember this one is when there is no friction. And then when there is friction, all these ones. So a situation like that, in that case, it simply means that friction will be going this way. Once they tell you the body is moving upward, but there is friction. So it's going to be this plus this now. And this one is the one going upward. So this will be this minus this one. It will be equal to the total force. While a situation where they tell you that the body is moving downwards, which means that upon there is force applied, that means this body is heavier. In that case, since this is moving downward, friction simply means force opposing motion. In that case, friction is no longer going to be this way, it's not going to be this way. So for that reason, it will simply be this. Remember, the direction the body is moving is in charge. It will always be the one that the other ones, forces are subtracting from. So it will be this minus these two. So if I know it, we need to know, or we need to remember. Anyway, I don't think it's in your scheme of work to do friction, but it's still in your scheme of work to do dynamics, and dynamics cuts across friction. So that's why we are touching it. So once you know that, I think the only big deal there is to now know that friction is equals to normal reaction, because it's a force. Force normally is also equals to normal reaction. So for that reason, if we introduce coefficient of friction, we have mu and N on its own. I want to do that N thing again. So you see how we got it. N on its own. Can I clean this?
Yes.
See what I said? I said, if I have an object on an inclined plane, and that object is like this, that the force is acting on this object, see something, see something. Surely you know that if I place this object on horizontal surface, this object on horizontal surface will simply be, this is going to be the x-axis, this will be the y-axis. If there is gravity or normal reaction on this, it will be this way. As it's acting downwards, as force is acting downwards, there will be another one acting upwards, normal reaction. So if that be the case, notice that this side of this is this, and this side of this object is this side. So we say that this side is x-axis. This side of this object is what is here. This side is what is here. So if that be the case, as this thing is like this, the x-axis of this is this way. And how we get that x-axis to be mg sin theta and n to be mg cos theta is what I want to prove now. If that is the case, let's say this is the vertical line. If this is the vertical line, everything here is the n, because as the force is acting this way, it's giving it as well, which is what I've done here. Now notice that the weight of anything on earth goes, no matter how you are placed. The minute I am standing like this, my weight is going this way. If you place me like this, the weight of my body will now come and find the direction straight down. That is why it will change, trying to bring me down. So as this thing is like this, the weight will still go down straight. It's not taking any angle. It's still straight. And if that is the case, as I've done this, so let's say this is the weight. Let's say this is the normal reaction I've gone through. Now notice that if what I have here, equilibrium, if what I have here, I come and trace it down here. That is parallel lines. So this is now going to be the x-axis. Remember, this is n, And remember that this line, what brought about this line is G, weight, G, the gravity, G acting on it, the weight of this thing is going to, so bring mg as well on this, weight of it ahead. So if you check, you see that you've drawn a triangle, like this triangle, inside this thing. So pull out that triangle, see that you have something like this now. You have here to be mg, you have here to be n, and you have here to be x. That's what you've done. And what will be the angle? Which side will be the angle? The side that will be the angle is going to be this side. Why? On an inclined plane, once you see an inclined plane, it's like a pendulum. The angle made is with the vertical. The angle made is with the vertical, not the horizontal. So anytime the angle is made with the vertical, so if we say that this triangle is like this triangle, they are similar triangles. The size is different, but it's the same position. So that means that the angle is here, theta. So if that be the case, we'll now go back to our secondary school drawing board. So means sine theta equals to opposite over hypotenuse. And what is the opposite here? Is x, the part facing the angle. The hypotenuse is mg equals to sine theta. Make x subject of the formula. X becomes mg, that is sine theta. That is why we say that anytime you see x, the part that wants to slide down, call it mg sine theta. Now n, the part, if this is a straight line, let's say this is a straight line, the part that as this thing is, the part that is next to it, the angle next to it, or you say the side that the angle is sitting on is the cos, the adjacent. So for that reason, we go back to our drawing board. Tan is equals to cos theta equals to adjacent over hypotenuse. And cos theta here, the adjacent is n. Yes, the hypotenuse is mg. N over mg. So if you make n subject of the formula, you now have that n is equals to mg cos theta. So that is how we have it, that anything that has to do with normal reaction is simply mg cos theta. While everything that has to do with x, the sliding side, is equals to mg sine theta. So as you progress, if you learn this thing, you don't have to come and be doing this thing to find it. What you just need to do is to simply know it. Just call the sliding side mg sine theta. Call the normal reaction mg cos theta. Very simple like that. So with that said, I want us to now notice that what we did for this inclined plane is when it's sliding down and when it's moving up. A situation whereby the force applied to this is so much that the force applied to this is so much that it is no longer sliding. So see, it is not sliding, the body is not at equilibrium. Like let's say you have this, then you see some setup where you now come and have something like maybe this thing like this. You now come and have maybe a pulley that connects this so that, let's say I have it like this, connects this so that you have another object on this particular thing like this. And in that case, you can now very well see that at equilibrium, when this thing is no longer sliding, they can ask you, what is the force there? How do you find it? So that is what I want us to do. So we are neglecting this. This is the body we are looking at too. We'll still come and check the force here. But remember, each one we're always doing, when you have bodies in dynamics, analyze each body separately. I said it from the beginning. So if that be the case, what it will simply mean is that in this case where they are at equilibrium, remember that the whole of this side is x-axis. this particular thing, if you take it and place like this is the x-axis. Look at it here. So everything here is the x-axis side. So if that is true, it simply means that in a state of equilibrium, at equilibrium, F, that force going this way will be equals to x. So it will simply be mg sine theta at equilibrium. This will also be mg sine theta. So both of them will be equal. So F will be equals to x, just like that. While the normal reaction on its own. So I remember first of all that in dynamics, force is equals to reaction, and when we introduce friction, force is equals to mu r. So if that be the case, we can also see that at this point, r itself, that is this part and this part, r itself is equals to mu. Okay, sorry, r, first of all, if you remember, r is the same thing as n. So let me use n, because some people will get confused. N is mg cos theta. Normal reaction. If you just want, you can just say reaction, but it's normal reaction. It's mg cos theta. So if that be the case, I can simply say that this is the same thing as saying, let me remove this thing. At equilibrium, F equals to S. F is the same thing. At equilibrium, this force here is equal to the force downwards. While this one is mg cos theta, there is this one this way. So if they ask you what is the force there, it's simply mg sin theta at equilibrium. Just like that. But a situation where they don't tell you, maybe to find something, because as we start taking questions, we will see. But you can now say there are questions where they tell you to prove mu equals to tan theta. So you can now say that F from F equals to mu n when we started. It will simply mean that this is the same thing as saying force here is mg sin theta at equilibrium. This one is mg cos theta at equilibrium. Shall you see? Then we don't know this one. The situation where we don't know this one, they now ask us to find it. All we need to do is to simply say mu now will be equals to F over n. Because you can say divide both sides by n to get this one to stand on this side. This will now be the same as saying mg sin theta all over mg cos theta. This can take care of this. And sin theta over cos theta is equals to tan theta. So mu, or coefficient of friction, is also the same thing as saying tan theta. And if I know that coefficient of friction is tan theta, notice something. If I come, there can also be a situation where they tell us to prove that mu, that force is equals to tan theta times normal reaction. Notice that if I have F here, and I have that this mu is tan theta, and I have n, that's n that is here, and n is the same thing as r. So F is the same thing as saying n tan theta, or you say r tan theta. So you can see it in so many books. There are wire questions where they tell you prove that force is equals to reaction times tan theta. So what they are trying to tell you is simply know that mu is tan theta. Then r is the same thing as normal reaction. You put it together, you get it. And how do you get it? Is by knowing that at equilibrium, force on that object on the upside will be equal to the one downside. Even normally, equilibrium is simply a state where the net force is zero. Any state where the net force zero is the same thing as equilibrium. So if that is true, it simply means that for you to have equilibrium, the force on the up and down will be the same thing. So that is how to go about proving it. So if you have a situation where this object here, you are told to find the forces on this object here, because that is what dynamics is. Dynamics is supposed to, what dynamics is trying to teach you is that as you know dynamics, just the way you know that in kinematics, you know all the equations of motion. So it's simply trying to tell you how to calculate force. Any angle you see a body or any position you see a body, how to be able to calculate the force on that body. If you see somebody standing, the way he's moving or the way he's doing, the force on that particular object at that or body at that point, how to calculate it. So if you look at this particular body now, yeah, looking at everything I've taught you so far so good, you will see that when an object is on a free or should I say vertical, for the fact that this object is vertical, remembering the principle, downwards here it will be expressing weight. So let's say this is m2, it will be expressing weight. So this is going to be m2g acting on it downwards, while this rope that is here is going to be a tension on it. So and anytime a body is vertical against something that is sitting down, so this is going to be something as saying m2g minus tension. And notice the tension on this object, at this point is the force on this inclined plane, which we already call mg sine theta. So this is the same thing as saying mg sine theta equals to ma. So minus m2g. And remember that this thing is the same thing as weight of that second body. So if that be the case, remember that at equilibrium, see, we said that at equilibrium, that means there is no change in direction, no movement. But assuming there is movement, we put A for something, we put A to be something. So at equilibrium, the A that is here will be 0. So 0 times m is 0 equals to minus mg sine theta. So by the time this Wt, weight on this object, will now be able to move over because mg sine theta. So you can now see that if they ask you what is the force, and do you remember that weight is the same thing as force? So that means that if they ask you what is the force on this object, the force on this object is simply the same mg sine theta. So once it's equilibrium, everything that has to do with this axis, the whole thing here, is simply mg sine theta. So that is what we just tried to prove now. Unless they tell you there is movement, assuming they said movement, in that case, you now know that your F can be something different, your A can be something different, and all those things. So, because for it to be movement, it simply means that the forces are not balanced. But at equilibrium, all the forces must be balanced. So, if it's so, this is how to go about it.
Please, what you think we'll stop here for now. You summarize, just give me a quick summary of what.
Okay. Okay. Okay, I'm coming. You know all these things if you love doing.
If you snap this thing as you are doing it, it will enable you to make it and everything.
Yes.
Is that what you are snapping?
Yes, videoing itself, not just snapping. Yes, you post it on YouTube. I have over 3K people always watching my YouTube channel. So see what I'm trying to say there? If I know that something is moving, that is called motion. Now when I come to something moving, I look at that thing, how it's moving. How that thing is moving. That one is called momentum. You are checking the mass and the velocity of that thing. That one is called momentum. But we will still get there, still under dynamics, but it's advanced, we'll still do it. And the impulse and everything. But when you are now saying, as that thing is moving, the forces around that thing that is moving, the forces around that thing that is moving, is now what you call dynamics.
Okay, it's dynamics talks more of, it's concerned with more of forces, more than it concerns more of forces. It's meant with forces. It deals with forces more than
The force, no, it's not more than, but it deals with the forces of motion. You can't talk about motion and not talk about force and say you are doing dynamics.
with dynamics is simply the forces of motion.
No, it's not. It's not. I know how you want to put it. It's not like that. If you put it like that, it's like you are trying to make it a simple something, and it's not like that. Dynamics is simply the study of the forces acting on a body. It's simply a study. So it's not like something you round up as just the forces of motion. The study of the forces connected to motion is dynamics. So it's more like saying forces on the motion or way. But when you are studying those motion and paying attention to the forces, you are talking about dynamics. So it's more like saying, even it's like an English word. In English, when you say that something is dynamic, it simply means that that thing can move, like that thing can touch different angles. Yes, he said this is a dynamic something. It's like when you think of versatility. But just that in versatility, you are touching everything, but nobody really knows the depth of what you are touching. But in dynamics, you are being to a point whereby you have something you always pay attention to. So that thing for dynamics in physics is simply what we call dynamics. So whenever you are dealing with motion, and you are not just you are dealing with motion and you are talking about maybe equations of motion, if you are talking about equations of motion only and not paying attention to dynamic, to force, that one is kinematics. But when you are not talking about motion and you are talking about the forces causing that motion, you say is dynamics. And that is why we say that instead of you thinking too much, the way you can round it up is simply dynamics talks about the laws of motion. When you hear this, when they tell you that something talks about law, it talks about governing the principles that govern motion. That's just the best way to put it. What are the principles governing motion? If somebody asks what are the principles governing motion, that person is most likely telling you dynamics without mentioning it. What are the governing principles of motion? What are the laws of motion? That person is talking about dynamics. So it's now under those laws of motion you now look at okay, under motion we have when we are talking about the forces acting on motion, and we have when we are talking about the equations, the mathematical aspect of motion. So when we are now talking about the forces of motion, that is talking about dynamics under the law. So I want you to, if you have to summarize it, or you are looking for a way to put it simply, the simple way is simply they are the laws of motion. They are the governing principles of the motion.
Just don't defend it. Just give me the
Come again, sir?
Just give me the exact definition of dynamics.
Okay, dynamics. I said dynamics is the study of motion.
Is the study
of motion with respect
of motion.
Yes, with respect to the force causing it. The study of motion with respect to the force causing it. So we simply say that dynamics are the laws of motion. Dynamics are the laws of motion.
That is I equal to
Yes,
What is this MRS?
MRS, that means mass reduced square. Mass reduced square. Now, another thing you need to understand is that under those laws, you now have three governing laws. The first law is the one that talks about states, that is inertia, the reluctance of the body to change position. So a body at rest will remain at rest, and if it's in motion, will continue to move unless acted upon by external force. That's the law of inertia. So, or you say tendency of the body to keep moving. So, but the main thing is the idea behind that inertia is that if something is at a place, it's even if air is blowing that thing, it works just like that can under your leg now that you put there. You see it's there, but the minute you kick its leg, it will move, but it tends to like give some reluctance. Even when you want to do something, even when you are doing certain things, if you put another person that is faster than you, and the person tends to be faster, it simply means that the person has a higher reaction rate than you, which means that your body, even though in your mind mentally you feel like you are moving, but there's a part of the body that wants to remain at rest. So that's what that law is saying, that everybody that is moving or that is at rest, in any position it is, it wants to remain there. It wants to remain there unless there's an external force. So that external force could be maybe application of forces, air or friction, all those natural phenomena. That's what the first law is saying. While the second law is not talking about direction. So if you check, they are all revolving around force. If something is at rest, the first one, if something is at rest or moving and an external force acts on it, you see that it will either stop or keep moving. That's force in the first place. That is the states, changing states. For the first law, it's about changing states, or it says states. While the second law talks about direction. Direction. So if something is simply saying that if something is moving, that any direction you apply force, that's the position, the direction or position that it will take. So if you push something left, it will go left. If you drag it right, it will come right. So that is it. So that law states that the rate of change of momentum is directly proportional to the applied force. And I told you that momentum simply talks about product of mass and velocity. And you know that when you have mass and velocity velocity means motion, mass means a body. So you say that a body moving at any given time will change its direction depending on the force applied to it. So that is how we derive that mv over t equals to force, which we later say that is equals to, that it gives us F equals to ma. So the second law is simply talking about direction. While the third law is talking about give and take. So it's talking about equal and opposite reaction. So it's saying that if you do something, you will get something. That's what the third law is saying. If you do, you receive. If you give, you receive. That's just what that third law is saying. So he's saying that to every action there is equal and opposite reaction. Or he's saying that to every force applied, there is an equal and opposite amount of reaction. So it's from that third law we will now derive all those things, like when the case is on the horizontal, when it's on the vertical, when it's on vertical and horizontal at the same time, when it's at an incline, and when it's on an inclined plane. Like in this case.
Now, this, let me just say, the meaning or definition is clear. The laws, the three laws is clear. Now, I think where the problem lies now is in this about this process, this to every action. This is what applies there's equal and opposite reaction.
Yes.
Now, it was listed that all these things evaluate or comes out. Now, what I'm saying is that I want you to say this is the formula when it is vertical, when it is horizontal. Get my point now. After this explanation of the meaning of dynamics, the three laws. Now, coming to this number 3, and it was where after these 3 laws now, we now talk about the formula when the body is vertical, horizontal, and so on. Briefly, so that one can just look at how to work the way it is.
Okay. Before I get there, I'm coming there. But see, before I get there, do you remember what position we put this thing? This thing that we did.
This one is equilibrium.
Equilibrium when is at an inclined plane, shouldn't? This is inclined plane.
Yes, this is equilibrium in inclined plane.
And
the formula is. And I just want to say this thing.
I know. Like before I do that thing you are saying, like I want you to remind me, because you know that there is something we call what you are taking, the capacity of what you are taking. I want you to remind me like how I went about finding the force on this particular body, now. You know that what you are saying now is like me rounding up all the formulas I've given you so far.
Yes.
Now what I'm trying to say is that remind me now currently. This particular body here, when it's at equilibrium, we derived all these things. But for this particular body of mass, how did we come about this mg sin theta? You know that the force on this particular body, that's what we did to find this now. So like, bring me to light how we did what we did, like why we did what we did.
There's a humanus tension. I think there was involvement of tension.
There is tension is on this rope now connecting this going backwards.
Yes.
That's it. Yes. Why this M2G is the weight of this body.
Yes.
And the T here, I said something. Why did I replace this T with mg sin theta?
Because it's going.
It's simply because at equilibrium the force here is equal to the force here, which is mg sin theta.
Yes.
And if that be the case, the tension on this is going to be the force that is on this road, on this axis. So which is mg sin theta. And by the time you put it M2G is the same as the weight of that second body, you minus it. And since it's at equilibrium, acceleration is 0. That means that this is the force. And I said that anything at equilibrium, the force is the whole sign will be the same. I want you to remember that one. With that said, let me recap the whole formula. Because the main idea of teaching is understanding. Not maybe you are just putting knowledge. Knowledge without execution. The person will just think they know it, but it's not doing anything. Alright, so let's recap the whole thing. And it's not really about vertical or horizontal. It's about understanding the cases. So, because we don't say you throw away the cases and then hope on just the formula. It's the cases. Those things I gave you, the diagrams and everything. The reason I gave you all those cases are so that you can have it in mind that when this kind of case comes up, this is what you need to know. This is what you need to know. And it's not every topic, because like you pass again and math, you understand like the principle that guides that person's learning. It's not everything that has just one line of understanding. It's not every topic that has just one line of understanding. There are topics that the main understanding comes from the diagrams or the cases, not a line. So if something is on a horizontal surface, let's say it's a body, just a body, of mass. The guiding principle on any body, horizontal, is simply if this body is this way, for it to move, what are the forces on it? And the forces on this thing, in this case, for a body that is horizontal, seated flat, is simply the weights going this way, the weights. But the minute that thing is moving and is not moving up, or maybe from up and coming down, it simply means that I need to not look at the weights. Unless they tell me somebody is sitting on this thing now, then I tell me the boy is sitting on this and is exerting force on it. Calculate the normal reaction. In that case, I will not be checking, and I say if a boy may be 5 kg, the weight of the boy down will be 5 times 10, that is G. So if the weight of this boy is this 50 Newton, what is the weight of this? Maybe 2 times 10 is 20 Newton. Then I tell me what will be the normal reaction? What force will the ground be exerting upward as this boy is sitting on this block? Since this is 50 plus 20 is 70, the normal reaction will be equal, force is equal to normal reaction. It will simply be 70. Normal reaction will also be 70 since force, the total force going downwards is 70. If somebody is sitting on this, the person weight is 50 Newton. This one is 20 Newton. On the ground is exerting 70 Newton. It will be giving it back, which is total of 70. But this is not what we are looking at once we hear there is movement. Remember, we are talking about motion. Unless they tell you, in this case, the way I've explained it. So the guiding principle when it's horizontal. So if you notice what I'm explaining, is more of a principle. Physics is a case, not mathematics. Physics is a case. The guiding principle is the case, not the case, not line. So if there is a case where this thing has to do with now movement, it can only move this way or this way. Just one object. We did not say, yeah, we know it can go up and come down, but they did not say go up, they say it's moving. So in a case where it's moving for just one body, it will be forward force. And the backward force, if this thing happens to move, is the friction. So it will now be forward force minus the friction will be equal to the total force, F net. And F net here is represented with M1A. Mass of that body. M1A is simply mass of the body. We say MA. Be sure that this is still recording. Okay. It's MA. But a situation where they did not mention this friction, they did not give you friction. Because it's not every time, just like if you are moving now, they say force is acting on you. Nobody wants to come and say, what is your friction? So in practical or reality, it's simply MA. So this is why we normally say force equals to MA. This force equals to MA is simply saying that any single body or the last body in any setup horizontally will always be just F equals to MA unless friction was indicated. Now, for a horizontal body, once there is movement, let's say we have two machines or two cars. And one is towing one. One is towing one. For the fact that these two cars are moving, even if they did not mention the force on this first one, provided this first one is the one moving this, or what the cars are moving, there is force that is making this thing to move, and the force is being generated by the engine of that car. So that means there is a forward force on this, for the fact that it is moving. So notice something, for horizontal body, in most cases, horizontal body, you don't come to start checking the weights, horizontal body, unless you are told. So it's more like saying, for horizontal bodies, you focus on the force and the tensions, unless it is specified that there is force on that body, they are not asking you to calculate the normal reaction, like just like when I started. So if that be the case, for horizontal body straight and there is movement can go only this way or this way. And whenever something is horizontal, what you are checking, movement horizontal, what you are checking is the forward force and the friction. While if something is vertical, what you are checking is the pulling force and gravity that wants it to come down. If that thing is moving up, it's going against gravity. So in this case, the first one, there is flotation on this rope. So the first body, always analyze the bodies individually or specifically, one at a time. So call this one the first body, call this the second body. You can choose to call this first body, second body, no problem, but analyze this separately. The first body for M1, it will be the forward force minus the tension force equals to M1A. It will be the force moving this forward and then the tension of this rope, because as it's moving, this thing, assuming this rope tends to be, should I say, strong enough that the car can't move, you see that it won't move again. So that's why we put it. Why for this M2, the last body is always going to be, this is the forward force for this body. T, assuming they mention friction to be T minus F equals to MA. But situation where they do not mention friction, and in most cases they don't mention it, T is just equals to MA. That is why I said that the last body may be given setup of bodies or just a single body, provided it has to do with horizontal movement. The last body there, or just the body there, is always going to be just the T, the tension force, or the force equals to MA. Just like that, because it only has to deal with friction. And if friction is not given, there is no backward force there. It's this way. So this is for horizontal setup. But whenever there is movement on the vertical, let's say they tell you somebody is falling down. If somebody is falling down, in that case, where somebody is falling down, there is nothing bending it up. That person is just going to fall, and the only thing acting on that body is just the weight. Let's say a ball now is coming down, straight down. I don't want to start applying what's it called? Projectile motion. The force here will simply be F equals to the weight. F equals to the weight. But when I have two bodies, that's when we now start to look at the tension force and the main force. So let's say I have a pulley now. Let's say I have a pulley, and this pulley is carrying two bodies. Let's say this is M2, this is M1. This will tend to move this way. This will tend to go up. The bigger body will tend to drag the smaller body. And if that be the case, then thank God for this. This will lead us to what we call lifter questions, lifts. So if this is the case, if this is going to pull this down, the part that is coming down is always the higher part. So the weight of this is what is coming down. So weight of 1. Weight 1 minus the tension here equals to MA. While this one is weight 2 and this is M1G minus C equals to MA. And for this particular body, this one, since it's going to go up, it means tension is higher than it. In that case, tension will be up minus the weight equals to the force. That is the force. This thing equals to means that is the force. So M2A. So it's said as T minus M2G is equals to M2A. Somebody might want to say, why is E equals to A? Why is the A there and not G? The A there is there because of the fact that it is moving. And it's not just that it's moving, it's simply saying that is the total force there. So that's M2A. Why I'm using M2 is because the masses are different. So this thing means this and this are the total force, and force is equals to MA. So instead of writing MA, you just represent the M2 there to say that it's the mass of the second body. So with that said, I want us to touch what we call lifter question. So this is for when the body is vertical. For lifter question, when you hear a body on a lift is going up or is coming down, the minute you hear a body on a lift is going up, a body placed inside a lift is going up or is coming down. If it is going upwards, and here that is a lifter or lift, if it's going upwards for lifter, notice something. If this is the lift and this body is going upwards, you can see that in that case, the body itself, the body inside this thing, is going to be disobeying gravity. G here will be negative. So, and this is M, mass of the body. So put it together, it becomes mg. And the extension. And because it's going up, that means that the rope inside that lifter, however it is built, is more. So it's taking it up. In that case, upward means T minus M G is equals to MA. That is the total force there. So it's more like saying, it's supposed to be, yes, it's, in that case, it's saying the tension force is the upward force, is going up. Why? The gravity is trying to pull it down. This becomes the backward force. And that is the weight becomes the backward, because weight wants to naturally fall like this, fall down. But it's now going up, which means that tension is more, the weight is less. So in upward for lift, when it's going upward, you are thinking of it that the weight in terms of the weight is there. So making it instead of the formula, it will now become equals to MA plus MG. T will now be equals to MA plus G. You see this formula in most textbooks. In most textbooks, where they tell you that when the lift is going up, that T is equals to A plus G. I believe following the video I've made for this class up from the beginning to the last, there is nothing else left to learn under dynamics except for solving questions, because I've touched virtually everything that has to do with dynamics. I've even entered as far as the friction parts that I entered. So now when it's coming downwards, remember this is lift. So when it's coming downwards for lift question, any question on lifts, a lifter did that one. So it's more like saying this is the lifter. Let's say there is a body inside this lift and it's coming downward, which means that mg is obeyed. Weight is more for it to be coming down. It's not like it's weight that is dragging it down, but it's simply saying that by forces of nature, as it's coming down, all of its direction, all of its position is tending towards the ground because of the way it's built. So it is going in the direction of weight, and that means that weight is more. That means tension is less. So forward minus backward. So it will now be mg minus tension. So the key thing is to always identify the position something is going. If it's going to my position, I am going to be more. And if it's going against the other party is going to be less. So it's going to be subtracting. So mg minus T is equals to MA. That is the total force there. So by the time you want to make tension subject formula now, you can see that if I carry this T to go to this place, it becomes positive T and equals to mg is just still here. Now, if you carry this to come here, it becomes minus MA. So that this becomes M inside G minus A. So that's it. Yes, so for downwards lifter. So in our next class, we'll solve questions on it. Well, thank you.